Okay, so it's our pleasure to have Heikki back today. And so Heikki got his PhD from University of Jyväskylä in 2015, and then from 2015 until 2017 he was a postdoc at the Brookhaven National Laboratory, and then he returned to Jyväskylä, where he has been since 2017, and since 2018 he has been funded by the Academy of Finland. And today he's going to talk to us about exclusive processes as a probe of gluon saturation at the Electron Ion Collider. So, Heikki, please.
Okay, thanks for the invitation. So let's start by looking at the QCD phase diagram, how I personally like to see it. So it's shown here on the left. This is kind of the cold QCD phase diagram, now shown as a function of parton density quantified by 1 over Bjorken X and the resolution scale. And the interesting corner of the phase space, at least for me, the most interesting corner is shown here, where the scale is large enough so that we can do some perturbative calculations. And also the densities are so large that physics is non-linear, and let's say the evolution equations turn out to be non-linear. So in this very large density region, technically we say that, okay, alpha S log 1 over X is order 1, so you need to resum these kind of contributions to all orders when you are basically describing any scattering processes. And this means that, say, multiple scattering effects are important. So if you shoot a probe through the dense color field, then you have to include or allow any number of say gluon exchanges with the target. And experimentally, we expect that we are even getting some nice new toys in the coming years. So even though we already have nice data, as I will show, from HERA and from the LHC, then there is also a concrete plan at the United States to construct an electron ion collider in the same tunnel, basically, where RIC is currently colliding nuclei and protons. And one major task for this machine is to probe QCD in exactly this region of phase space. Now, I don't want to go into the details of US funding agencies and politics and so on, but let's just say that this new $1 billion machine it's looking good, that something that it looks good that it will be constructed within 10 years, let's say. And again, going back from this more technical, so let's say from this experimental column to the column on the left, let's say that the effective or to describe QCD in this corner of phase space that is probed at the EIC, for example, we basically need effective field theories that describe QCD in the region where multiple scattering is important, and these large logs of 1 over X can be conveniently resummed to all orders. And the effective theory of QCD in the high energy region is the color glass condensate, which is the theoretical framework I'm using also in this talk. Okay, so why an EIC? And the simple question is that photons and leptons are simple probes compared to, say, PA collisions at the LHC or at RIC, where you're probing the proton that you are using to probe the nucleus, where the densities are, of course, much higher than in the proton. Then you have a complex internal structure in your probe, in the proton. So it's not actually that straightforward to determine based on the measurements what's actually going on in the, let's say, nuclear wave function. On the other hand, if I have just a point like lepton that emits a photon, then the process is much more clean, and I can do many interesting measurements. Of course, the simplest one is just the total cross-section measurement. So I can do the most simple DIS measurement, ask what is the total cross-section for photon-proton scattering or electron-proton scattering. This basically tells me what is the total proton density in my proton. And at high energy, which is the limit that I'm taking always, there are basically only gluons in the protons and nuclei. So this measures the total gluon density. Also you note that because the total cross-section is related by optical theorem to the forward elastic scattering amplitude. So forward meaning that the momentum space scattering amplitude is evaluated at 0 momentum transfer. Then if you go to coordinate space, this means that you are basically just integrating over the whole transverse plane. So what you are seeing is the number of, say, the total number of gluons or density of gluons, but you don't really get information on how they are distributed spatially. Now, diffractive or exclusive processes, which is the focus in my talk, are different in a sense that now I require that I produce exactly one particle. In most cases, I'm considering a shape psi meson, which is a bound CC bar bound state. Now, in such a process, I can have a virtual photon emitted from the lepton. Then this photon somehow interacts with the target proton or nucleus, and I produce the vector meson. And then experimentally, I require that there is a rapidity gap, meaning an empty detector between the outgoing meson and the outgoing proton or nucleus. Now, in order to have an empty detector here, I hope you actually see my mouse. In order to have an empty detector between the shape psi and the proton, you cannot transfer net color charge, which means that at lowest order in perturbation theory, you need to exchange 2 gluons at least, which means that very approximately this cross-section is proportional to gluon density squared. It's not linear as the total DIS cross-section, but gluon density squared. So you also expect this to be much more sensitive to nonlinear effects. The other advantage is that by measuring the transverse momentum of the vector meson, you know what is the total momentum transfer in the process. And it's the Fourier conjugate to impact parameter. So somehow by definition, this is the process that measures what is the spatial distribution of gluons in the protons or nuclei that are probed in these high energy collision processes. Okay, so let's take a closer look of the vector meson production or exclusive scattering now in the CGC or color glass condensate framework. So of course the lepton, how the lepton emits a virtual photon is kind of a trivial process. So we throw it away. We don't. It's a simple prefactor basically in the calculations, and then we consider virtual photon proton scattering, or proton could be a nucleus. Now, at high energies, this is conveniently factorized such that first the incoming photon splits to a dipole. This is a QED process. You can compute that quite straightforwardly, and so you calculate the photon wave function, which describes photon to dipole splitting. Then this dipole somehow interacts with the target. The quarks propagate through the color field, and as I mentioned at the beginning, they multiple scatter, and at high energies, basically the transverse coordinates are fixed because, I mean, if you are moving at very large with a very large longitudinal momentum, then during the interaction you basically have no time to change the transverse coordinate. That's the reason why it's convenient to work in terms of the transverse degrees of freedom, like the size of the quark anti-quark dipole R, and B here is the impact parameter, and X refers to the Bjorken X approximately. Okay, so and then after this scattering, I still have to form my final state, which usually is the shape psi, and this requires some modeling because we cannot really compute the vector meson wave functions, but there are some phenomenological models for that. So then basically from these steps you can already construct the scattering amplitude for such a process. It's a convolution where you have the wave functions for the photon and the vector meson, and then part that describes how the dipole interacts with the target color field. This is something that we can describe from the CGC effective field theory. I don't go very much into those details. And then because this is written now in the transverse coordinate space, but what you actually calculate or measure is as a function of transverse momentum. So delta is the PT that the vector meson has after the interaction. Or yeah, then I have to calculate the Fourier transform from coordinate space to momentum space. And as I mentioned, the Fourier conjugate to the impact parameter is the momentum transfer. So you already see that this scattering amplitude is actually very sensitive to what actually is the spatial dependence of the dipole target interaction, how this function depends on the distance from the proton to the center of the dipole. Now these diffractive events can be divided into two categories that I'm going to talk basically throughout my talk. So let's see what these event categories are. First, we talk about coherent diffraction or coherent vector meson production. This means a process where my target remains in the same quantum state. So if I have a proton in my initial state, I have the same proton in the final state. And as already shown, like 60 years ago, to calculate such a process, what you actually do is that you calculate the average interaction of QQ-bar dipoles that have a fixed transverse. So the quark and anti-quark have fixed transverse coordinates, or the size is fixed, and then they probe the fixed target configuration. So the target can, of course, have different, let's say, the color charge can be distributed differently in the target in each event. And then if I calculate how the average, how this dipole target scattering on average takes place, I get the cross-section for the virtual photon, proton, or nucleus going to a vector meson plus nucleus. So this cross-section differentially momentum transfer squared goes like the average interaction or the average scattering amplitude squared. And because I first take the average and then the square, then this cross-section measures how the scattering amplitude actually depends on average on the impact parameter B. So you see this technically, if I calculate the average over the different configurations of my target here, then the scattering amplitude I had on the previous slide depends on how the dipole with size r on average interacts when at transverse coordinate B. So basically this is probing the average density profile of my target. On the other hand, I can consider a process where my final state, proton or nucleus, is different from the initial state. So basically I allow it to break up, but still requiring that there is a rapidity gap between the target remnants and the produced vector meson. So basically now schematically I can write the cross section such that I have a transition from initial state to final state, and the final state is different from the initial state. And this I can of course write by first allowing all the possible final states and then subtracting the case where the initial and final states are the same. So then this part basically is the coherent cross section that I just discussed, and then the first part basically is the total diffractive cross section. And so this difference is called incoherent diffraction. And what you actually get when you also take into account that you have to average over the possible initial stages, then the cross-section you get by taking the square of the scattering amplitude and averaging over the initial configurations, and then subtracting the coherent cross-section that I just discussed. So this incoherent cross-section is actually variance of the scattering amplitude, and as such, it measures how large event-by-event fluctuations there are in the target configurations when I evaluate the diffractive scattering amplitude. So it tells me how much my target structure fluctuates. Because now target structure measured by a quark-antiquark dipole, how much that fluctuates event by event. So then we did the exercise already a couple of years ago with Björn Senke. So there is plenty of data from HERA with proton targets. So considering photon-proton going to a shape psi plus proton, the data is basically probing Björken X roughly 10 to minus 3. Now, we can calculate from CGC, as I mentioned, how the dipole interacts with the proton. So what we first did is that we say that protons are spherical, just some Gaussian density profile, more dense at the center, then gets more dilute. Then we basically sample random color charges and solve the Young-Mills equations to obtain the dipole scattering amplitude that I denote by n in this talk. Now, on the left, what I'm showing is some HERA data from H1. The black symbols are the coherent cross-section, and as I mentioned, this cross-section is sensitive on the average interaction with the target. And this blue dashed line here is the calculated coherent cross-section using protons that look something like this. Of course, this is just the one example, but if I just sample this kind of round or spherical protons, they look almost the same. But then the incoherent cross-section, the measured incoherent cross-section is shown by the open symbols here. And then if I take these protons that look, for example, like that, and calculate the incoherent cross-section, we get way too small result compared to the HERA data. So then our idea with Björn was to say that, okay, but what if the proton has some spatial density fluctuations? Of course, the first idea that you get is that, what if the proton consists of 3 hotspots? Maybe, I mean, you can think that you have, say, valence quarks that radiate small x gluons. You can also play with different geometries, but I'm not going into that. So then you can parameterize such fluctuations by parameterizing the size of the hotspot and how far from each other they on average are, and then write that your density profile is just some of these hotspots. So this is what we did already some years ago, and now this has become an industry. Different groups have been refining this kind of an approach. So as you can guess now, I have 2 data sets that are sensitive to, on one hand, the average shape, and on the other hand, on the amount of fluctuations. Then I can constrain these 2 parameters that go into the distribution of hotspots to constrain the event-by-event fluctuations of the proton structure at small x. So then on the left-hand side now, the solid lines are what we get by adjusting the fluctuating proton shape parameters, then to get somehow the best fit scenario. So this is the black line here is the coherent cross-section. It's almost the same as in the case where we didn't have any geometry fluctuations, because on average they don't really change the proton shape, but on the event by event they of course do. And then this thin line here is what we get for the incoherent cross-section. Now it's like 2 orders of magnitude larger, because the geometry fluctuations of course increase the variance of the scattering amplitude significantly. One example of this fluctuating proton configuration that goes into this calculation is shown here on the cover of the recent CERN magazine. So you can imagine that if one proton looks like that, and then you sample thousands of them, I mean, you kind of see that it looks very lumpy, or it has to look quite lumpy to describe this data set. Now, this is something that we already can do with the HERA data, and then in the future, what we can do at the EIC, for example, is to more closely take a look at the Bjorken X dependence, so how this fluctuating structure evolve as a function of energy, and then by varying Q squared, we can also vary the distance scale. So when you go to higher Q squared, you can look at the smaller distance scale effects. And of course, something that HERA couldn't do is to look at the nuclei with A larger than 1, because there is very little, or there is no data, no high energy data available except for proton targets in electron ion collisions at this point. Okay, so I mentioned already saturation or nonlinear effects in my title. And of course, now one question that you should ask is that can we already from the HERA data see effects of nonlinear dynamics? This turns out to be quite difficult somehow, basically because shape psi is quite heavy. So shape psi mass squared is already quite a large scale, and it then becomes difficult to see any nonlinear effects. Technically, we showed that already, or analyzed that like 2 years ago with PIA. So what we did was to first look at models that include saturation effects, known as denoted by SAT here, and then the linearized version that doesn't have any nonlinear dynamics included. In both of these models, you can get an excellent description of the precise total cross-section measurements from HERA, shown here on the left. So you can't even see the two overlapping curves here. But okay, this is total cross-section, which only probes roughly the gluon density to the first power. So then you may expect that if you look at the exclusive process, which is gluon squared, you may see some differences. On the right-hand side, I'm showing total shape psi production cross-section as a function of center of mass energy for the photon-proton system. Data is from HERA and also from the LHC. And then the solid line is with nonlinear effects and dashed line without. Of course, there seems to be quite a large difference, but then actually the energy evolution is very similar. You only have some overall normalization difference. And then in all these calculations, normalization is quite difficult to predict because that requires you to model the non-perturbative vector meson wave function. So you would really want to see more like some effects in the energy dependence, but those you don't really see even at the LHC kinematics. So message we got is that you basically need to look for higher gluon densities than what you can see in photon-proton. So you need to go to nuclei.
Can I ask you a question?
Yes.
Do you mind going back to the, yeah. No, I was wondering about how to match this description with the standard Pomeron exchange, because this is like real photon.
Yes. Okay, yeah, this data is for real photon, yes.
Yes, so I imagine that you are dominated by the soft Pomeron exchange, and that will completely predict your energy dependence. Is that right? So how these different pictures match with each other?
Yeah, that I don't really have a good answer. I mean, how I deal with this interaction is perturbative, because I calculate the dipole or the photon to dipole splitting using just perturbation theory, and then my quarks propagate through. I mean, so then when my okay, when my quarks propagate in the target color field, that kind of corresponds to the Pomeroy exchange.
Yeah.
I mean, you can in somehow in dilute. If the density is not, I mean, if you can neglect non-linearities, it's basically the BFKL Pomeroy exchange.
Yes, that's my problem. So I would imagine that in this case you should see the soft Pomeroy, so that honest to God.
Well, I mean,
so yeah, but I mean, yeah, just my intuition.
Okay.
Now, I was wondering in that case, since you're talking about perturbatory calculation, what plays the role of the hard scale?
The mass of the tape side.
And that's enough, okay.
Because then if I somehow, I know that I'm producing a tape size, so my dipole needs to be quite small. If my photon splits to a large dipole, then it's highly, highly unlikely that that large dipole forms a tape size. So then somehow the mass of the tape size controls that also the dipole size must be like 1 over mass of the meson.
I see.
Yes, good. So we clearly want higher gluon densities than what we can see in protons. Roughly, I mean.
I also sorry.
Yes. Now I can.
Okay. I also have a question about that, about the previous slides, and yeah. So normally for Gypsum production, I would expect the model dependence is very strong. I mean, the uncertainty should be very strong. Should be very large. So I don't know. Do you have you tuned the parameters about the Gypsum production?
Yes. So basically, the largest model uncertainty here goes into the tape size wave function. So how I need to somehow describe how a dipole forms a tape size. This can be, I don't, maybe something up to, let's say, 30-40% effect on the normalization.
Okay, so have you tested if you use different models for Gypsum production? Would it change your conclusion or something like that?
So here, basically the wave functions that we have available in the literature for tape size, they result in based on almost an identical energy dependence and T dependence, but it's mostly just a different normalization. So
the shape will be
the shape has always been quite identical. I will actually quickly come back to that later in the talk, but somehow the bottom line is that at least everything that we have been used, it mostly affects the normalization. So we are quite confident that all the shapes, like energy and T shapes, are quite robust.
Okay.
Yes. So to get larger densities, so the density we characterize by QS, the scale that tells you when nonlinear effects become important. You can think about that by just as density, some measure of density. Now, of course, the density scales like A to 1/3. If you have a nucleus, then you have A to 1/3 nucleons line on somehow aligned when you propagate through the nucleus. And then the density also goes like x to minus lambda, where lambda is something like 0.2 or 0.3. That's what we know from here. Now, larger A is cheaper than smaller x. That's basically the reason why we want to build an electron ion collider and not just like a Hera with much larger center of mass energy. So you can of course reach the same densities by going to smaller x, but this is, as you know, very, very expensive and difficult. But now to demonstrate what kind of effects you can expect if you have nuclear targets, we can look at ultra-peripheral collisions. So these processes have been measured at RIC and at the LHC in recent years. So the idea is that we can have, say, two nuclei colliding with large enough impact parameters so that the strong interaction is suppressed, and what happens is that you can decompose the electric field of one nucleus into photons, and then these photons, they turn out to be basically real photons. They then interact with the other nucleus. Now we can measure, for example, shape side production. So you can collide two lead ions, and only thing you see in the detector at the LHC is one shape side. The kinematics is such that basically, if you measure if the shape size produces at different rapidities, you are probing different Bjorken X values. Now, this is one of the first measurements by the CMS collaboration in such a collisions. The data points are shown here, and if you just take the Hera measurements for photon-proton scattering and shape side production in these events, and then scale it up by taking into account the different geometry. So instead of having the proton form factor, you have the form factor of the nucleus. Then you approximately would expect even like factor of two higher cross section than what you actually measure. So there is clear hint that in these events you have strong nuclear effects that in my picture is due to the nonlinear dynamics.
Excuse me, the J psi is detected through di-muon pairs or the lepton pairs?
I think it's usually from the muons.
From muons, yeah.
Yes.
Well, at CMS, it's definitely only muons, yeah.
Yeah, but in Alice also?
Alice is probably both.
Depends. That must depend on the kinematics, because Alice has muon detectors only in the forward.
Yes.
Yes. So they have been using both.
Well, that's why I guess they have two bins in rapidity. So one probably is in the central detector, and the other is the muon detector. So probably they're using both.
Yes, and then I think they also have had data at some recent. This is quite one of the first publications, but then the recent data, there is more differential data more rapidity bins. I think what they can do is also take like one muon or one lepton, like I guess electron in the central barrel and the other electron in the forward, or something like that.
Okay.
Okay. Now we can of course also do this kind of calculation from the CGC framework. What I'm showing here on the left is now at the EIC kinematics, not all the way up to the LHC kinematics. I'm showing what I call the nuclear suppression factor. So this is the cross-section, shape side production cross-section with nuclear targets, in this case gold, normalized by the cross-section of proton targets, and then the normalization factors are chosen such that if you have no nonlinear effects, this ratio is exactly 1. Now, the different curves, I don't want to go into details. They correspond to some different wave functions for the shape psi. So this kind of controls or shows you what kind of uncertainties we get. Now the uncertainty is not huge because this is a cross-section ratio where at least a large part of the wave function uncertainty cancels. It is one case that clearly predicts very different suppression than the others. This is completely non-relativistic description for the shape psi, which is probably not the most realistic. So it's a significant suppression also at the EIC kinematics that we expect. even though shape psi mass is not really small, so I mean it's non-trivial that you actually see some significant suppression.
Sorry, what is this gray band? Can you go back?
The gray band is in one of these wave functions. We also have available the actually the wave function we developed in this paper. We also have some uncertainty analysis available. So we know how the different parameters are correlated with each other, and the parameters are constrained by the decay width. So basically, in this one particular calculation, we were also able to actually quantify the model uncertainty, which gives you the gray band around the black curve.
Okay.
And also with nuclei, you can of course do this geometry analysis. So this is the simulation at the EIC kinematics in exclusive shape psi production with gold targets. The points here that show this diffractive pattern are the coherent cross-section. The difference between the solid and open symbols is that either nonlinear effects or saturation effects are taken into account or not. And then, as I mentioned, this coherent cross-section is sensitive to the average distribution of small x gluons. Now, if you say that they are distributed as dictated by the Woods-Jackson distribution, so basically this is a simulation. So what goes into the simulation is that okay, nucleons are sampled from Woods-Jackson distribution, and then in the simulation you add some realistic uncertainty estimates for the EIC, and then you can do a 2D Fourier transform back to the coordinate space from here, and on the right, what is compared is the Woods-Jackson, which is an input distribution to this simulation, and then the solid line is what you get out. So of course, I mean, if this in reality differs from Woods-Jackson, then you see something else. But this is a demonstration that at the EIC or with the EIC precision, you can very accurately map also the nuclear geometry at small x. I should emphasize that the LHC, like when you do UPCs at the LHC, then none of these experiments is capable of measuring these cross sections differentially in T.
Is this, what nucleus is this?
Gold. And then these lines show the simulated incoherent cross sections, where you actually expect even larger saturation effects. But in the interest of time, I'm not going more into that. Then, of course, we have plenty of nuclei between gold and protons. Actually, last week, STAR showed shape psi production of deuteron. So they did deuteron-gold collisions, and then they measured exclusive shape psi production. Now they cannot really separate coherent and incoherent cross section. So the symbols here show the total measurement, and then what you can see overlaid here is prediction from the recent paper I had with Björn Senke that apparently the reference is actually missing. Anyway, so we modeled, we had two different sets of deuterons, either the case where proton and neutron have no substructure, so they are just some Gaussian blobs of colored charge. In that case, we got the red line here for the total cross section. I should emphasize that this is such a large momentum transfer that basically the incoherent cross-section dominates, which, as I discussed, probes really the amount of fluctuations in the wave function. And the black line we get when we have the proton and neutron having a substructure also that is constrained by the Herat shape side data. I had to show this plot where this black line very nicely agrees with the data, because when the experiment, I mean, I took this part of the slide directly from the STAR presentation, and so this is not my sentence, but they actually wrote that curves are not fits; they are only overlay. And when experimentalists have to write this when they are comparing to your theory predictions, I mean, then you are, of course, this is kind of funny. So I had to show that. This is important because then we can do like deuteron gold, like high multiplicity deuteron gold collisions, and ask the question if those can be described using relativistic hydrodynamics. So like if quark-gluon plasma is formed and so on. And if you apply hydro, you need to know the initial spatial energy or entropy deposit very, very accurately. We also actually, in case of proton nucleus collisions, we demonstrated in this paper that if you take this fluctuating proton shape constrained by Herat data, then you can describe some flow effects or correlations that you see in high multiplicity PA collisions by assuming that quark-gluon plasma is formed. Of course, it would be nice to be able to separate between coherent and incoherent processes here, but this is not possible, at least yet at RIC. But with the EIC, this kind of more precise and more differential measurements are possible. Yeah. Finally, the last topic related to vector mesons, related topic is going to more differential observables. So far, this has been only measuring the total cross-section as a function of momentum transfer. Now, I'm showing you just a couple of preliminary plots from the recent work we have in progress with Kosik Roy, Farid Salazar, and Björn Sönke from BNL, where we are looking at electron vector meson or electron photon correlation. So we consider this is DVCS. So I'm calculating a process where I exclusively produce a photon. But for tape side, this can also be done. This is a rather busy plot because this is just a couple of plots from my notebook and not really anything that's polished for publication. But now we measure or we calculate the cross section as a function of the azimuthal angle between the outgoing photon and the outgoing electron. And what we are interested in seeing what kind of modulations there are. So the cross section has a component which doesn't depend on the angle. And then there are two modulations, cosine phi and cosine 2 phi modulations. And then now we can calculate these modulations. And now this is interesting because it kind of shows how some structure that you have in the coordinate space or some dynamics in coordinate space, how that propagates to momentum space. So basically, you remember I have this dipole amplitude that tells me how a dipole with size r, how it interacts with the proton or nucleus, and then b is the impact parameter, so distance from the center to the center of the dipole. Now, if this interaction doesn't depend on the angle or the orientation of this dipole, then what I get is the left-hand side plot. Let me walk you through this. So the black solid line is the average cross-section as a function of momentum transfer. So this is the part that doesn't depend on the angles at all. Then I have cosine phi modulation with some prefactor. This prefactor is the red dashed line that is shown here. It's smallish. I mean, all these modulations are small compared to the average one, but maybe still measurable. And then the dotted line is the cosine 2-phi modulation. This is very small. In this calculation where there is no dependence on the dipole orientation. Now, if I include cosine 2-phi modulation in the cross-section, basically saying that when the dipole is aligned parallel with the impact parameter, the scattering probability is higher. And then if it's perpendicular, then this is the minimum of the scattering. Scattering is less likely, or the least likely. In that case, basically almost the only thing that changes is that now the cosine 2-phi modulation, the dotted line, becomes much more important than here on the left-hand side. And what this tells now, so I see very different cosine 2-phi modulation depending on what kind of dynamics I have in my coordinate space interaction. Now physically, this tells me about either you can talk about some transverse momentum dependent Gluon distributions like elliptic Gluon TMDs, or the elliptic Wigner distribution. The Wigner distribution is the one that depends on both the transverse coordinate and the transverse momentum transfer, or the transverse momentum of the gluon. So what in this work, which is currently in progress, we are discussing or analyzing how well you can constrain these more differential gluon distributions by looking at the lepton-meson or lepton-photon correlations. In this calculation, we just plug in by hand this angular dependence, how this interaction depends on the angle, but we can also calculate that angular dependence explicitly from the CGC framework. So this becomes this result is more clear, maybe more clearly shown here. So if I, instead of showing just these different components, I can quantify the cross section by having cosine phi and cosine 2-phi terms with some coefficients. And then I can plot the coefficients as a function of momentum transfer. On the left, again, the case where there is no dependence on the angle between, or the orientation of the dipole in the scattering amplitude, then the elliptic modulation V2 is basically 0, and then you see a very different behavior when some modulation is included in the coordinate space corresponding to an elliptic Gluon TMD, which is included in the calculation. So in this project, we are kind of seeing how large signals you can expect to see at the EIC, and then how well you can actually constrain something like the elliptic Gluon TMDs or the Wigner distribution of the EIC. But yeah, this is still a work in progress. Okay, for the last couple of like 10-ish minutes, or say last 10 minutes, I wanna flash something we did by somehow continuing this trend of going more differential. So I started by discussing just the exclusive vector meson production as a function of momentum transfer. Then the last couple of slides were about correlations. So I had dependence on both the momentum transfer and on the azimuthal angle between the lepton and the meson or photon. And then finally, of course, not maybe most, but even more differential is to look at the dijet production. So you can require that instead of a vector meson, you produce two jets. The kinematics is such that the delta is the recoil momentum. So K1 and K2 are the momenta of the two jets. And then this is the recoil, so the momentum transfer to target. And P is basically the it kind of measures the average ZPT. And in this recent letter, what we actually did was to simultaneously describe both inclusive die-set production and diffractive die-set production. And we are considering kinematics where basically the coherent contribution is small, so basically the nucleus or proton breaks up, but it's still diffractive, so large rapidity gap and no net color charge transfer. This the other case where the nucleus doesn't break up, then that was analyzed in some other previous publications that I don't consider here. This is a rather busy slide given the time I have left, but anyway, the message is actually quite simple. So if I calculate die-set production, what I have again is the wave function now only for the photon to dipole splitting. I don't need to model how the vector meson is formed. And then I have Fourier conjugates to different transverse momenta. So impact parameter is conjugate to recoil momentum, and the dipole size is conjugate to the jet momentum, the average jet momentum. And then there is some operator. And this operator is slightly different in inclusive and diffractive cases because the color structure is different. So if you look at inclusive jet, you don't require any, you sum over all the possible colors for these two jets, and then you can write this operator in terms of some correlators of Wilson lines. Also, the dipole amplitude that I have been discussing so far, it's a correlator of two Wilson lines. So basically, trace V, dagger V. Now you also get some structures like traces of four Wilson lines, but we know basically how to evaluate those. Now, if I consider diffractive scattering, I require that these two jets have the same color. So I mean, there cannot be net color transfer. This is color neutral. So this die-jet system in the amplitude must be color neutral. And then I get some different operator structure. And then you can compare inclusive and diffractive cross sections, where now the nonlinear effects affect differently, and then as such measure or constrain the nonlinear dynamics. This I just go through very quickly by only looking at this 2D plot, where what I'm showing is again this kind of modulation, V2 modulation, but now it's modulation in the azimuthal angle between the momentum vectors P and delta. Now I just similarly as before, if I have some dependence on the dipole orientation in my scattering amplitude, I get some positive or non-zero contribution here. But what we showed in this work is that even if you neglect that contribution, you only consider orientation independent scattering, you still get a sizable modulation in the die-jet production cross section, some tens of %. So this is a contour plot. The contour show the modulation in %. And this is due to the multi-Gluon correlation. So basically you have in the scattering amplitude structures where you basically correlate 4 gluons at 4 different transverse coordinates. And these complex structures give rise to these non-zero modulations. Also, what we did is to look at inclusive case where where it's somehow more straightforward to also see the effect of, well, maybe not more straightforward, but also a nice way. There is a nice way to see the effect of multi-gluon correlations. So if you go to this kind of particular kinematical limit, you recover TMD factorization. So where the cross section can be written such that you have a transverse momentum dependent Gluon distribution and transverse momentum dependent elliptic Gluon distribution. And these you don't look at the formula, but these distributions are basically functions of the 2-point function or the dipole scattering amplitude. So they don't really measure the multi-gluon correlations. Now, if I calculate the inclusive Dietzsch production cross section, which is shown here on the left as a function of Dietzsch momentum, then I can compare what I get if I do the full calculation by actually evaluating these multi-gluon correlations, or if I just from the same framework go to the TMD limit and basically neglect all the multi-gluon correlations and higher point functions. What is plotted on the left is the ratio of the cross sections that you get in this TMD limit divided by the full cross section. So basically, if I look at, say, Dietzsch production of gold with recoil momentum 3 GeV and Dietzsch momentum, let's say, 0.5 GeV, then you expect a factor of like 3 difference on the Dietzsch cross section. So there is a huge effect in this kinematical region where the multi-gluon correlations, these multi-gluon correlations have a huge effect on the Dietzsch production cross section if you are in this particular kinematics. Similarly, on this second plot, I'm showing the elliptic modulation V2. Now the difference between the black and the red lines is that again the red line is what you get by doing the full calculation, and then neglecting the multi-gluon correlations gives you something like well, you see significantly different modulation. So measuring this both inclusive and exclusive Dietzsch production is definitely an interesting probe of nonlinear dynamics in the future EIC. Now let me skip the last slide and go to my conclusions. So DIS processes, especially exclusive processes, both in ultra-peripheral collisions and in the future EIC, are powerful probes of nonlinear QCD dynamics because they are sensitive to nonlinear dynamics, and there is also this nice possibility to probe the geometric structure of hadrons at small x. And then there is progress towards more differential observables like lepton-photon or lepton-meson correlations, and actually correlations of 2 Dietzschs, or actually not 2 Dietzschs, but Dietzsch correlations in Dietzsch production between the jet momentum and the recoil momentum, where it's also possible to probe the multi-gluon correlations that when you are measuring the multi-gluon correlations you can measure when you are studying the cross section outside this kinematical region where this TMD limit can be derived. The last slide that I kind of skipped also discusses that if something like diffractive to inclusive cross-section ratio is very powerful probe because nonlinear effects affect the diffractive and inclusive cross-sections differently. So these cross-section ratios are usually referred as kind of smoking gun of gluon saturation at the EIC. So thanks for the attention.
So, do we have questions?
Hi, Heikki. So
Hey.
I think I have a very naive question. So regarding the JPSI production, so since as you say that this is heavy enough, right? I mean, it has like, I don't know, 3 GeV. So if you take the square, which is usually more relevant, you know, it's 9 GeV square.
Yeah.
So if you have a QS square, which is around 2, I don't know. I think you said it yourself. So why is this process sensitive to saturation? Because I don't know, except if the wave function of the, you know, if there is a good overlap in the wave function of the JPSI, then it can be sensitive to saturation. If no, because, you know, if you want to be sensitive at saturation, you would need dipole sizes in the process which are like of the size 1 over QS.
Yes.
But 1 over QS is rather large compared to, I don't know, to 1 over the M-psi square. So why is the process sensitive to saturation eventually, or it is not?
Well, yeah, it's a quantitative question, of course. So it's a quantitative question. So I mean, okay, this is the nuclear suppression slide I showed. I mean, it's not a huge effect. It's 20% effect, because I mean, somehow, if you think about photon JPSI overlap, I would say that in most case, I mean, most part of this overlap, you are clearly in some sense probing too large scales or too small distance scales to actually be sensitive to nonlinear effects. But there is some extent in this overlap that also reaches the let's say 1 over QS region in case of nuclear target, which then results in some suppression or some linear effects in the cross section.
Okay, thanks. So you just say that even though the scales are different, there is some overlap, some significant overlap.
Yes, I mean, yes.
Okay.
I mean, if you just take, I think if you just take exactly 1 over m squared size dipoles, this would look very different.
Okay.
There was one naive thing I had in my mind. So I think on slide 3, I mean, maybe this was answered later on one of the slides. I mean, I was just wondering, so you were saying there's this psi v wave function, and I think during the slide you were saying that this is somehow the kind of a wave function that you have an idea what it is, but you don't. But there is somehow no explicit form for it. But I mean, did I understand correctly that slide 11 was where you were somehow going through? Are these now the same wave function, or?
Yes, so different curves correspond to different JPSI wave functions.
Okay, yeah, because this is somehow what I was wondering, that how do you quantify the uncertainty, because you have a function and you need to plug in some kind of a function which you don't quite know what it is.
So actually in this solid line, that the only calculation that has an uncertainty band, that band comes from the fact that, so this is based on non-relativistic QCD, including some corrections. First relativistic correction. So basically there are 2 parameters that are some long distance NRQCD matrix elements. And these matrix elements are determined by the decay width data. Basically you look at the JPSI and eta meson decays, and then you can constrain those long distance those long distance matrix elements. But of course not precisely. I mean, you have some data that has uncertainties, and then these parameters that or these matrix elements then also get some uncertainties. And then actually these uncertainties are also correlated. Now, these matrix elements tell you basically what is the wave function at the origin, the value of the wave function at the origin, and its derivative at the origin. And that's basically all you know and then then you kind of based on this information you extend that to finite sizes also, because that's what you actually need in these calculations. But yeah, so in this one case where you have the uncertainty band, the band comes from the fact that the numbers that go into that particular wave function are constrained by experimental data, and as such these parameters have some uncertainties. I mean, of course, also in other wave functions, they are constrained by the decay width data, but then these parameterizations don't have the uncertainty analysis included. So basically, you can think that you have kind of different functional forms, or you have different ways to construct the vector emission wave function, and always when you construct it, you also need to fix some non-perturbative parameters by comparing with the data. So in principle, all these curves should have some error bands just from the fact that the decay width data doesn't precisely constrain the parameters. But I mean, these are just somehow widely used phenomenological parameterizations. For example, this one, and somehow the authors never reported the uncertainties for the parameters, and then nobody has really developed those.
Okay, so this is actually kind of a deep and tricky thing to do.
Yeah, the fundamental problem is that the decay width probes the decay width is sensitive to the wave functions at the origin. But then, or origin meaning zero size quark anti-quark pair. But the zero size quark anti-quark pair doesn't really interact with the proton because it has no net color charge if I calculate vector emission production. So basically we can only constrain the wave function in the region, or we precisely know the wave function only in the region where it doesn't which doesn't actually enter into cross-section calculations at all.
All right. Thanks. Okay. Do we have any further questions? Okay. If not, then let's thank Heikki again. Okay. So I think so according to my records, the next seminar should be on 16th of June, and it should be by Kepani Raya Montagno. I hope I pronounced this correctly, at 2 p.m.